Hello student, welcome back to lecture series on Legendre's differential equation, which is from the linear differential equation with the constant coefficient, which is from subject M3. We have started lecture series based on the entire topic from M3. So if you are interested to see this video, do check in my playlist. In my today's video, I'm going to explain to you all example based on Legendre's differential equation. For more example or theory part, you may check in my playlist. Okay, so in my last lecture I explained to you all how Legendre's differential equation it works. Okay, so today it is the time for solving the examples. Okay, yes, let's go for the solution. I written this question over here. Similar type of the question you will get in your university question paper for 4 to 5 marks. Okay, so make sure that these are the easy type of the questions. Okay, yes, now what we do whenever we have 2x plus 1, like whenever we have ax plus b, we go for the substitution. Okay, whenever we have ax plus b, we go for the substitution. Now see that whenever we have ax plus b, okay, I will explain to you all first of all Legendre's differential equation. Okay, then we go for the solution. Whenever we have ax plus b into dy by dx, whenever we have x plus b into dy by dx, we write a into dy. Okay, whenever we have this term, we write a into dy. Okay, again whenever we have x plus b bracket square d square y by dx square, we write a square d into d minus 1, okay, into y. Okay, this one is a x plus b bracket square. So if you have cube, that means you have to extend the values only. Okay, whenever we have cube, x plus b cube d cube y by dx cube, then we write a cube d into d minus 1 into d minus 2 into y. Okay, so this value we replace here whenever we have Legendre's differential equation. Okay, so let's go for the replacing all these values. So that means x plus b dy by dx, so we replace 2x plus 1 dy by dx here. Okay, so we replace 2x plus 1 dy by dx. What we are going to replace? 2x plus 1 dy by dx as a. What is meant by a into dy? A into dy means a which is equal to 2 into dy. Again observe it carefully how I am writing this part. See that we have to replace 2x plus 1 dy by dx, 2x plus 1 square d square by dx. Okay, whenever we have ax plus b dy by dx, we write that a here, then capital dy. Okay, yes, now see that x plus b, 2x plus 1 dy by dx, I written two coefficient here as it is. Okay, and a capital dy over here. Okay, yes, so similarly go for the replacement of these values. Okay, so what the next step I'm going to write here? 2x plus 1 bracket square d square y by dx square. Okay, 2x plus 1 bracket square d square y by dx square. So I'm going to replace this one here as a square d into d minus 1. Okay, what is the value for a which is a 2, and a square means 2 square is a 4. Okay, d into d minus 1 into y. Okay, these are the value we have to replace here in order to reduce our given Legendre's differential equation into the given auxiliary equation. Okay, yes, go for the replacement of value. 2x plus 1 square d square y by dx square, replace it here, 4d into d minus 1. Okay, this one is the value. Again minus 2 into 2x plus 1 dy by dx into 2 dy. So we are going to write 2d y. I'm going to take it out here. Okay, I'm not writing y, it is here, minus 12. Okay, out of bracket y, which is equal to 6x. Okay, now see that we have to replace the value for x, as we know that x can be replaced by. Okay, so we are going to replace 2x plus 1 as, so it is for the value of x. Okay, so we are going to replace as we done it in our Cauchy homogeneous linear differential equation, as we consider x as a e to the power z. Okay, so now we are going to consider that 2x plus 1 as a e to the power z. Okay, we are going to replace 2x plus 1 as a e to the power z here. Okay, yes, then z which is equal to log of 2x plus 1. Okay, z which is equal to log of 2x plus 1. Then we write a dz by dx which is equal to 2 upon 2x plus 1, okay, log x as a differentiation 1 upon x, and d by dz put as a capital D, okay. This substitution you need to remember all time, okay, that we are going to do everywhere. So need to remember this substitution, okay. We done it same, but the variables are different in our Cauchy differential equation, okay, Cauchy linear differential equation. Now see that 4d into d minus 1. So x, I want to replace x also, okay, because if you are taking every term in the form of z, then means you have to replace x also. So how can you get the x here? You have to solve x from this term, okay. So how can you write x here? X can be written as e raised to z minus 1 by 2, e raised to z minus 1 divided by 2, okay. Now see that x I taken here, e raised to 1 to the other side, e raised to z minus 1, and 2 multiplicand goes to the denominator. Put this x over here, okay, e raised to z minus 1 by 2, okay, 6 into e raised to z minus 1 by 2. We go for further calculation. So see that 4d into d, 4 times d square minus 4d, okay, 4 times d square minus 4d, multiply 4d under bracket, minus 2 multiplied by 2, minus 4d minus 12 into y, which is equal to 2 1s are 2, 2 3s are 6, 3 into e raised to z minus 1, okay. This one is the next step. Just go for the calculating terms now, okay. 4d square minus 4d minus 4d minus 8d minus 12, okay, minus 8d minus 12 into y, which is equal to 3 e raised to z minus 3, okay, 3 e raised to z minus 3. Now see that I reduced our given Legendre's homogeneous, I reduce our Legendre's differential equation into the auxiliary equation of the form f of d into y, which is equal to phi of x. Now later on it is easier to find out the roots, okay, it is easier to find out the roots. So let's go for finding the roots here. Now see that as we have 4, it is everywhere same, na, take it common to the other side, so it will be helpful for finding the root. So I'm going to write d square minus 2d minus 3 into y, okay, but out here 4 out here, 4d square minus 8d minus 12, so 4 out here, take it outside here, 3 by 4 e raised to z minus 1, okay. Yes, this way I replace this term, okay. Yes, find out the root for d square minus 2d minus 3, okay, d square minus 2d minus 3, which is equal to 0. This one is our auxiliary equation. For finding the complementary function, find out the roots for this auxiliary equation, okay. So if you're going to go for the roots, so you will get the minus 1 and 3. So we want the two number where multiplication minus 3 and their addition is a minus 2, okay. So we get the d as a minus 1 and 3 here, okay. So if you don't know how I found these roots, go and check in my previous playlist, okay. You will get the idea how can we find the roots, okay. Yes, now I got the d as minus 1, 2, minus 1 and 3. As we have roots are real and distinct, then we write complementary function. What we write? Complementary function c1 e to the power minus 1 x minus x plus c2 e to the power 3x, okay. This one is our complementary function. This one is our required complementary function. Now it's time to work for the particular integral. We know that particular integral can be written as 1 upon f of d into phi of x, okay. So 1 upon f of d. What is the value for f of d? We are going to replace f of d as a d square minus 2d minus 3, okay. This one is our f of d, d square minus 2d minus 3. So how this one is f of d? We learned already, f of d into y, which is equal to phi of x, okay. This one is f of d, this one is y, and this one is entire phi of x, okay. Yes, and what is the value for phi of x? Replace this one here, okay. So phi of x is a 3 by 4 under bracket e raised to z minus 1, okay. So take 3 by 4 out here, 3 by 4 outside, okay. 1 upon d square minus 2d minus 3, okay, e raised to z minus 1. I am going to write as a e raised to 0, okay. E raised to 0 means it is 1, okay. Why I am writing this one? Because we know that whenever we have e to the power ax, we replace d as that a, okay. So similarly do it here and similarly do it here, okay. Yes, so e raised to ax means we have e raised to az, okay. It is not the term of x, it is the term of z. So we write 0 as a 0 times z and z as a 1 times z, okay. So take that 3 by 4 out as it is, keep it is here, okay, would d 1 upon d square minus 2d minus 3 multiply by e raised to z minus 1 upon d square minus 2d minus 3 multiply by e raised to 0 times z. Okay, replace d as 1 here, so 3 by 4, 1 upon 1 minus 2, okay, 1 minus 2, which is a minus 1 minus 3 minus 4, okay, which is a minus 4 e raised to z. Okay, that means e raised to z by minus 4 we get it here, minus, replace 0 here, 0 0 it goes to 0, that means 1 upon minus 3 e raised to 0 times z, okay, like this. Yes, now let's go for the next part. 3 by 4 out here, minus 1 e raised to z by 4 plus 1 by 3 only, okay, e raised to 0 z means it is 1 only. Okay, this one is our required particular integral. Okay, so as we have complementary function, this one here complementary function, this one is a particular integral. So complete solution, we write complementary function plus particular integral, put this value here, particular integral here, and complementary function here. Okay, you will get the entire solution for this example. Okay, I hope you all have understood this solution. So nothing it is difficult, it's one of the easy example. You will get this question for 4 marks in your SPPU question paper, so get prepared with this example. Okay, so I hope you all have understood everything here in my today's lecture. Even after, if you found anything difficult, confusing, challenging, let me know in my comment section, guys. I will come up with the similar videos. Or if you want to see more videos, comment me in my comment section which topic you found difficult. I will upload similar videos. So thank you everyone, thank you for my today's lecture.